And we're back. All right. Everybody's with me so far on everything we're talking about here? Mm-hmm. And you understand, because I just threw out these concepts and I didn't write anything about it, but as far as what I'm talking about when we're talking about reading an oscilloscope, what an oscilloscope is. Mm-hmm. And we talked a little bit about, the peak, reading peaks and not peaks. And we're good? Okay. Well, then we can just move right on.
How far leads to the peak will you get your most efficient average?
Oh, that's a good question. Usually about 3 potatoes in. Oh, man. Could you, huh?
Clocks out here.
Now I was curious what the next slide is. Oh, well, that just tied everything right in. So should have went to that. So using that circuit that we just talked about, well, that's how you'd work a d'Arsonval movement and keep the current always going the same way. So whether it was positive or negative, it's just going to work its way through like we did a little bit before. And so it's always going to be going in this way. It's got the little arrow going that way. It will always go that way, no matter if this is positive and negative or if this is negative and positive, because of the rectifier bridge circuit. Follow?
Yes.
Good. Glad we did that one. All right. Oh, yeah, we're going to get to that one. Don't worry about that. Okay. Point 3, because I don't know why. All right. Let's see. Why I put note, I don't know. Note that, and you know this, all voltage meters need current flow to register. Why do you need current flow?
You need to measure the resistance of it to find voltage.
Say that again?
Current flow times the resistance of the meter is voltage.
Okay, true. Why do I need current flow?
To find voltage.
Mechanically speaking, why did I need current flow? Huh?
To move the needle.
To move the needle. Had a little coil in there. If you don't have current flow, then you didn't make an electromagnet. You don't have an electromagnet, the needle never moved. So you got to have current flow. Everybody follow? Not lying to me. All right. So you need current flow for the meter to work. And what's going to make the needle go further to the right?
More current flow.
More current flow. So voltage meters. Voltage meters actually read current flow. Actually read current. Current flow is a little redundant, but I said it, so current flow. Calibrated to show volts. Calibrated to show volts based on Ohm's law. You may have heard of that before, which is current is proportional to voltage. There's a lot of things in aviation where it tells you one thing, but it's based on something else. Like it's telling you voltage based on current flow. Something might tell you gallons per hour based on pressure. Those are the only 2 things I can think of. So I want to say there's a lot. I meant 2. All right. Most meters have about 100 degrees of usable range due to principles of magnetism. to tell you, but I wrote it here. So magnetic force acting on a substance is inversely proportional to the distance, which is to say that the further away you get from a magnetic source, the less influence or pull that it actually has on something. So we'll be all technical. Magnetic force acting on a substance, substance is inversely proportional to distance. Which again is to say the further the distance, the less the force. So meters can only read a certain range before the magnetic force is actually out of play in it. Oh, goody. I was thinking, hey, I got to talk about this thing. Oh, I am going to talk about this thing. Can I move it?
Move it, move it.
I like to move it. All right, these little beauties. We got to throw this in here at this point right here. Wheatstone Bridge. The Wheatstone Bridge circuit. Do I have a picture of a Wheatstone Bridge circuit? Let's see. No, I don't. So I shall draw one. Wheatstone Bridge circuit. I have an example. And let's see here. And they always make them in triangles too. I mean diamonds. So. All right. What's that right there? Switch. And I have to put that little dog leg there because that's kind of where my picture goes when I'm talking. So, all right, Wheatstone Bridge. Oops, let's label it. R1, R2, R3, and R of X. This could be R of P. And we're looking good. Label that A, put that B, we'll label that C, we'll label this one D. Points A, B, C, and D. So Wheatstone Bridge. This is a widely used type of circuit. Used type of circuit. Used for measuring resistance. So R1, R2, and R3 are precision variable resistors. Are precision variable resistors. And by variable resistors, the way I picture that one is they're fixed for our purposes, but if you needed to do this, you can go into it and do micro adjustments to them so that you can balance it out perfectly, because they have to all be perfectly balanced. So if one is off a little bit, then you're going to get current flow in a way you don't want it. So, well, I don't do too much detail on this. R of X is the resistor to be measured, is the resistor to be measured. So a galvanometer, there's that word again, or a needle movement is at G. And geez, that's what we're gonna, yep, condition. So it's there to indicate the condition of balance. So this is S1, switch 1. Probably should have just left that out and drew it kind of closed right there. So 1, 2, and 3 are precision resistors. What the hell is R of P? I don't even write that in there. My notes suck. All right, so if R of X is what you want to measure, then you kind of look at it like these are your probes. Like here's your black probe right there, or red probe, and then your black probe comes in the other way. So this is external to the meter. So now we're kind of looking at how does this meter work? And you know that inside of the meter, you do in fact have a battery inside the meter. That's why it really screws it up when you add a battery onto these two right here. It doesn't like it. It's got its own. So what happens is if R1, 2, and 3 are balanced out perfectly, then what you get is when current flows through here, you're going to get a reading on your meter because you're out of balance between one side versus the other. If 1, 2, 3, and 4 were all perfectly in balance, then you don't get movement across. Well, it's all in balance. You're going to get a reading on your meter. So I was trying to think of a good example, but I don't have one in my head. But anyway, that's I'm just going to leave it right at that because, like I said, well, I got some more. A, B, C, D. I wrote that. D. Say a meter is inserted into the circuit. Inserted into the circuit to indicate the condition of balance. To indicate the condition of balance. If the bridge is properly balanced, if the bridge is properly balanced, there is no difference of potential. There is no difference of potential, and meter will read 0. When does your meter read 0 when you're reading, when you have it on the ohm scale? You short out your leads. 0. So technically the whole thing is in balance. And so that's what you're doing with, it might be RP in this particular case. You're zeroing out to balance it out. So what you're doing is every time you short out your leads and you zero it out, you're balancing out the bridge circuit. And so now your leads are shorted out right here. So you have to balance it so that one side is equal to the other. And then when you take it off and you put it on a resistor, you're out of balance. Right here, you're out of balance. So current then tends to flow through the out of balance and back around.
Is this what's in the Simpson meter?
Yeah.
What's the, what is it that we're treating when we're seeing?
I think it's this right here.
Okay.
Not 100% on that, but I'm pretty sure it's that right there because that's the unknown here on this. Because the bridge circuit has to have, or it could be you're balancing out, I don't think, because these are precision. You could be balancing one of these out to do it, but you're balancing out this little bridge circuit so that you want to get no flow through the meter. You get it across, you come up through C, B, R1, A, and back down, or through C, D. It's going to flow through this bridge circuit, but not through D and C. So if nothing flows through B and C, then you're in balance. And the meter will have no current flowing through it, so it'll say 0. All right, but then you take off your leads and then you put on a resistor. Okay, now it's out of balance technically. And so what happens is current will now flow out of balance because R1, 2, and R3, RX are different from one side to the other. And so because it's different, you get current flow through B and C, B and D. Current flow through B and D causes the meter to move, and the meter is going to tell you what you are reading. These little bridge circuits show up all over the place. You're going to see them again and again when you're looking at schematics and stuff. I don't deal with them too much in this class because this is like the only time it comes up for us. But I want to say it comes up again in fire detection systems and things like that. So if the meter is out of balance, the meter will show an indication. I should say if the bridge is out of balance, not the meter, the bridge. That makes more sense. If the bridge is out of balance, the meter will show an indication. Proportional to the out of balance. And the more current that flows through the out of balance, the more the needle will reflect. Is what?
Could it be that RP is meant to balance out the resistance of the galvanometer, the internal resistance?
Maybe.
Because that way they're like this.
That would make sense. But you also have to have a zeroing out thing, so.
Yeah.
I don't know. All right, like I said, you will see it, maybe not quite in this detail, but you will often see 4 resistors in that triangle variation with points B and D shown, and you're looking for voltage or something to go through B and D. You can use it in different ways to indicate an out of balance. What?
B and D is the bridge?
Yeah, well, the whole thing is called a bridge circuit.
Okay. Oh.
The triangle part, the diamond part is a bridge circuit. And the idea is when you're out of balance, you get flow through B and D. Trying to think what other functions you could do. I wonder if exhaust gas temperature probes work that way. They might. All right. Proportion out of balance. All right, moving on. Sensitivity. All right. If anybody asks if you had sensitivity training, you can now say yes. I don't believe that I'm going to ask you any questions on the test about a Wheatstone bridge circuit, other than maybe I would say when it's out of balance, what happens? Well, current flows. There are many questions on the test about sensitivity, and this is where we've been headed today with what we've been talking about, meters and how they're going to work. And you're going to be expected to understand the sensitivity issue and how to dissect it and create it. So sensitivity is defined as the amount of current flow needed to create a full scale deflection. Needed to create a full scale deflection. So Simpson has a DC voltage sensitivity of what, Tyler?
20,000 ohms.
Listen to that guy. 20,000 ohms
Per volt.
per volt. So we're talking about sensitivity and full scale deflection. So to get a full scale deflection, you're talking about 20,000 ohms for every volt you're trying to measure. So if I was trying to measure 1 volt, how many ohms is in that circuit?
20,000.
1 volt would be
20,000.
20,000. Oh, look, I did the math right here. So 20,000, or 200, yeah, no, 20,000, I said it right the first, 20,000 ohms at 1 volt equals how many amps? Well, how in the hell would you ever figure something like this out? Ohms who? Never heard of the guy. Give it to me in the amps. One, two, three, four, five. There we go. 0.0005 amps. I don't want to say that all the time. How many milliamps is that? 0.05 milliamps. So I don't want to say that. I want microamps. Now, how many microamps is that? 50 microamps. All right. Hopefully everybody can see that I'm talking the same thing. 0.00005 or 0.05 millis or 50 micro. It's all the same number. Everybody with me?
Yes.
All right. And everybody knows where I got that from.
20,000.
It's that Ohm's law guy where it's E and I and R, where I knew the E was 1 and I knew the R is 20,000, so divide and you get to 0.005. Okay. Let's see. Let's try this. So if I had it on the 2 point, jeez, I wrote the 2, so 2.5 volt setting, what would a full scale deflection be?
50,000 volts.
All right, so it's 2.5 times 20,000 equals how many?
50,000 ohms.
50,000, 50K ohms, 50K ohms, right? All right. On the 10 volt setting, how many ohms is that?
20,000.
That's 10 times 20, 0 equals 200K. Oh, what is my amps over here? How many amps for the one before that?
Would it be the exact same?
I'll figure it out.
Well, if you set it up as a ratio, it'd be the exact same. It's still 50 microamps.
50 microamps. Well, how about here?
50 microamps.
Okay. Is there a problem here?
You're multiplying the top and the bottom by the same number, so it's essentially the same fraction.
Yeah, but how do we end up with 50 microamps every time? Is that a problem? Why do I want that? Because that's the full scale deflection. So what's inside of the meter? A coil and a little magnet, or a coil and another coil. And you'll want to do full scale deflection, which goes from 0 to full scale. How many amps should it take? Every single time, it should take 50 microamps to go from this side to this side. Because it's the same coil, it's the same spring, it's the same magnet. Nothing's changed. So then why are you switching the dial? changes the internal resistance so that it sets it up. So when it gets to the needle, it doesn't go bing like some of you let it do. You guys have been fantastic, actually. I'm telling you, probably the best class I've ever had with some class. I mean, they're just like, switch it, and that needle just sits on the edge and vibrates. I'm like, So I look at it and they'll turn it off and back on. Then they switch leads, then it does it the other way. And I'm just like, oh my gosh, what did this meter do to you? Who hurt you? All right. So what did I put here? It is not, I put the note that it is not the actual voltage of the circuit measured, not the actual voltage of the circuit, voltage of the circuit measured doesn't make sense. It's not the actual voltage, but what do we actually, we're trying to measure voltage, but what is it really measuring across or using to do that?
Correct.
Yeah. Yeah, I'll just leave that there because, all right. So let's see, meters have different volts on each scale. So meters may have different ohms per volt on each scale. We're just talking about our Simpson meter because that's the one we're using. So the Simpson is 20,000 ohms per, I'll just put per volt on all DC settings. This limits the current consumption, limits the current consumption of the meter and leaves the circuit relatively unaffected. And I'm going to stop right there. Yeah, because the next thing takes a little bit of time once you have a fresh brain on this one. So I'll let you do that. Then I'm going to talk about something a little bit different here for a few minutes. Then I'll circle around and write more about this particular topic later. Tell me when you're done writing. By the way, I started a new little group of videos called How To. And so anything you can think of, you want to send me something, hey Kevin, you should make a, 2 to 3 minute video on how to, I'll do that. So I made 3 of them and threw them in there today. How to measure voltage, how to measure resistance, and how to measure amperage. They're very short. There's not a lot of information. It's just the very basics. Finished. All right. So some of you have now started working on your schematic for the motor project, as we call it. And this is the week that we're going to talk a lot about, which is next after we talk about meters, is about diagrams and things like that. But to kind of keep you going so that you don't get all bogged down in this, and because it's a good time, when we talk about aircraft electrical systems, and I've talked about this before, but inside of the aircraft, mine happens to be right underneath the panel. You can reach your hand under and touch it. There's a strip, depends on the airplane, mine's probably that long, of aluminum or copper, and it's called the bus bar. The bus bar. And the bus bar is hot. It has got positive on it. And it usually comes in, well, let's be honest about this. Let's try and draw it. So I would have a master switch. A master switch. A master switch. No, I gotta do this right. Let me think about it, because I wasn't planning on doing this. I have a master switch. We'll put it right here, master switch. So when I turn off the master switch, the airplane, it dies. There's no electrical to anything except the clock. And the clock comes right off the battery. And so I got my battery, speaking of my battery. Right next to the battery, I have a big old solenoid. I think it's hot. I had to do an experiment on it one time. We were working on a customer's airplane, and I forget what the electrical problem was, but they were very concerned about the fact that they're having some problem. And by the way, when he went to the baggage compartment where the battery was and grabbed onto that master solenoid, it was hot. So I flew mine around and then for an hour, and then jumped out and measured my master solenoid. It was about 100 and some degrees on a reasonably cool day. So there's a solenoid there that, because of the way I drew it, has a wire that's going to go up to the bus bar. All right, and so when I talk about a solenoid, and I'll draw one right here, a solenoid is something that has very little wires, very small, less than 18 gauge, say 20, 22 gauge, little small wire that goes around a coil, which are wrappings of wire. And when this is energized, it creates a electromagnetic force. And we'll say that the magnetic force pushes. So when it's on, it pushes. I'll put a little arrow to indicate pushes. And then there'll be a steel bar, literally a bar of steel, very thick, very heavy, can handle massive amounts of current. And it's going to have some, obviously, connectors inside of it. And now I can use some very fat wire right there, because, man, I got a big old load, maybe a starter or whatever, right? Calm down. So I have this little tiny wire, and it's all the way back inside the baggage compartment is where my battery is. And so the cable that runs from the battery up to the bus bar is the size of one of your fingers, because it's going to carry the whole load. And we'll do that. So look, I can do this. There. Very big wire. Comes to the bus bar. We'll do that. And because I'm going to do that, and then I'm going to change my mind about this. So hope you're using pencil. And we'll put the battery back here in the tail of the airplane where it is. There's my battery. All right, battery. Oops, I got to finish connecting it. So we got the big old wire, comes down. There we go. Big fat wire, back of the airplane. Now I got to switch this, right? Well, I don't want some Frankenstein's monster switch in my cockpit, right? Big old knife blade with a handle on it about yay long. Clunk. I want a little tiny switch up here in the cockpit, right next to where I'm at. And so to do that, let me think. Let's run a little wire, just a little tiny wire. Run it around to right here. And let me see, there it's going to get power. And that one's going to run back around, back to the back of the airplane to right there. And so when this is closed, this master switch, that's the master switch right there, and they're red. When I close that, current is going to flow through this wire, and it's a little wire, hardly weighs anything, a little number 18 wire or something like that. It's going to run through there, provide electrical current through here. It's going to push this bar, and this bar is going to push up and do what? Why am I having such a hard time with this? Black. Fucking that. Wow, what is it, like some sort of charcoal thing now? Perfect, this is exactly what I wanted, thank you. Oh, I know, ink flow died down, there we go. Got it, okay. See, like every time I run across that, that's why I hate that thing. Okay, so that goes up, this bar connects, yeah, there we go, connects, and I have current flow going all the way through here to the bus bar. Bus bar is now live, got it?
Mm-hmm.
So can you see how I controlled that big old fat wire with little tiny wires? And that's the purpose of a solenoid. So there we go. So now I got a solenoid. Well, I have a starter on the front of the airplane. Just asking for trouble now. There's a starter up in the front of the airplane. It's a starter motor. How am I going to control that starter? Well, can't really do that because I got a big old start switch, right? Huge, because it's a lot of current, right? Big old button about yay big. No, I have a little tiny button. I have a little tiny button up in the cockpit, which actually it's on my key. It's so small. And the little contacts inside that key are very tiny. So I've got this starter. Well, guess what's on the starter? A solenoid. So once again, we have a, asking for trouble, big old wire off the starter. It's right next to it. And on the starter, I got, that has to come, oh, that comes actually, if you will, let me see. That actually goes to right here. And what's right in there in that space? What kind of switch? A solenoid. So I got the bar, and I got the solenoid and the ground. Well, got to control that. So what controls that? A switch. What's that little triangle mean? Momentary. So I can just put it on the bus. So now when the master switch is on, the bus is live, and now that switch is live. So if I push the switch, it's going to energize this right here, and the starter is going to go. If I turn off the master, the bus dies, and I can push the starter all day long. Starter doesn't work. But notice how I just got one very big wire, ran all the way up front, tie it off into the bus, so I'm not running wires back and forth and back and forth. I can do it like that. Follow?
The
All
bus
right.
doesn't have a lot of amperage.
What doesn't?
The bus, since it's connected.
Bus has a lot. Bus is going to run everything. See, where did I get the power for that switch? Right off the bus. And guess what else is going to go on the bus? Let me see. I have this one. This can go to my landing lights. This can go to my nav lights. This one's going to go to my taxi light. This one's going to go to my radios, which is going to be GPS, transponder, everything else.
So you don't burn your stuff, you use resistors and
No, there's no resistors.
it just connects straight.
Well, this landing light's going to go In my plane, it's going to go forward through the firewall and down to the front cowling, and there's going to be a landing light. And then the nav lights are going to come out, they're going to parallel out to the red light, the green light, and the white light. And the taxi light, well, that's going to go to a taxi light, ground out, up in the cowling. Radios, they're just going to tee off into 3, 4, 5, 6. How many radios I have? I've got radio 1, radio 2, nav 1, nav 2, GPS, transponder, the Garmin's, the G5s, all that stuff. So they're just going to keep branching off and branching off and branching off, however many I need off of that switch. Now, what I didn't draw in here, which I should have, is the switch doesn't actually come right off of there because we forgot something. Circuit breakers. So the very first thing you want is the circuit breaker, then the switch. Circuit breaker, switch. Circuit breaker, switch. Circuit breaker, switch. It's literally, the circuit breaker is literally screwed to the bus bar. There is no bus bar, then wire, then it's screwed right to it. There's screw holes in it, and they just screw it right there. That's why it's right. That's why I can reach up and grab it underneath the instrument panel, because all of my circuit breakers are right there. So if I just reach around, I can touch it. I wouldn't recommend it, but you can. Yeah.
Could you think of the bus bar almost like a pool of amps that you can like draw from?
Sure.
So like each little component is only going to draw like 1 amps of your
Yep.
50 available or whatever.
Yep. Because
That's why you won't like burn up the little relay with 50 amps, because it's only going to ask for 1 amp.
yes. Yep. And we can take it one step further. We also have, so that's a big wire. What is that? The generator. So now I just drew the generator in there. In all truth, the generator is going to have another switch that's going to control, there'll be a switch that controls the field. Everything else, I've just simplified it here. But the generator, will say, feeds into the bus. So once the generator's working, guess what the battery is? It's a load. So once that generator starts going, it's going to start feeding into the bus. And this is going to start going that way and feeding back to the battery and doing what to the battery? Charging the battery. That's why we can say a battery is 12 volts, a little more than that, but the generator is always going to be 14 volts. Generator's got to be more than the battery, so that when the generator or alternator is working, it's feeding into the battery. If the battery and the generator are the same voltage, then the battery never gets charged. Well, it only gets charged up to that low amount. If the battery is more than the generator, then if you didn't have protection, the battery would actually drive the generator. Generator becomes a motor, which gives you extra horsepower in your motor when the battery drives that. So it's like a trolling motor, yeah.
Some solenoids are designed for continuous duty and some are military duty. Can you comment on those and maybe how you could tell the difference if they were?
I don't know how to tell the difference other than part number. So what he's saying is some of these solenoids are made for continuous duty, like this one back here. If I go for a 1 hour flight, how long does this one have to be closed and working? 1 hour. My 1 hour flight, how long is the starter solenoid going to be engaged? Hopefully not more than 30 seconds. So that's a light duty, intermittent duty, we call it, while this one is continuous duty. I don't honestly know the difference between them other than part number. I would just order my part number. They're obviously going to be, if there is a difference, they're going to be made different. It's highly probable Cessna just uses the same one. It's easier to make one continuous duty and sell you that one for everything than it is to make an intermittent and go, well, you should use this here.
You don't know any process of checking, ohm resistance or anything in there that you could, if you had two?
I do not. You go by part number. Then what if it doesn't have a part number? Then I'm not using it. Because that would be bad. All right, so do you understand, hopefully, the function of a solenoid and how it was wired in and what made it work and how you would make it work. Yeah, I don't want to just draw a motor and show you how to do it because I'm being like, well, then I just did your project for you. So, but that's the basics of what a schematic's going to look like.
Is there a functional difference between a solenoid and a relay?
Okay, difference between that's probably a really good question. Difference between a solenoid and a relay. It's going to depend on what you read. So I use the term solenoid. Sorry, I should be using a relay. This should be a relay. This proper term be relay. I said solenoid, so relay. Relay. A solenoid, to me, is so a relay is something where a small amount of current controls a large amount. All right, so call that a relay. A solenoid would be like your electric door locks in your car. It moves something up and down. So that's proper term to be solenoid does some sort of mechanical function. A relay is the exact same thing, but it controls electricity rather than a button or a mechanical thing. Yeah, but they both are exactly the same thing other than that in my book. Yeah.
In an airplane where you've got to hook up like a GPU, it's got a generator or an APU or something like that, transferring power sources, would it just be a couple of relays where you transfer, say, from you're running on the cart?
They put a lot of them. Well, like my airplane does have a ground power receptacle on the outside of the plane, and a lot of them do. And so there is a relay attached right to it where it's got two receptacles. One is the positive, one is the negative. And right off the positive, it goes right up to its own relay, solenoid. And yeah, relay is the word I wanted, which then goes right to the bus bar. I'm just drawing it here because I ran out of room. So when you plug in the ground power, it automatically activates a relay that closes, relay that closes and energizes the bus bar all on its own. So once that's plugged in, that aircraft's live. You
Without
can't,
hitting the master
you don't
switch.
go in and the master switch on Cessnas. That's the way it is.
I just always kind of wondered like how that all of the information that's loaded up on.
Oh yeah, but when you get
You
into,
don't lose any of that in that momentary loss because there has to be a split second where
There is a split second where it goes.
it kind of and then it switches over. I've just always been curious as to what's going on there, and there's always like a very audible click.
yeah, there really is. Yeah, you're working on the 757s, right?
6.
767s.
But I mean, it's like every airplane. Like I feel like you can hear pretty.
Yeah, it's a pretty significant little clunk. I don't know which one are you talking about.
130 is that you can see.
Yeah.
You can see it when it clicks over. It
Yeah.
dims down real quick
Right.
and pops right back up.
Yep.
So is that like one opening and one closing, like
Yeah.
in unison?
Yeah.
Interesting. There's just not enough.
I would imagine though, like on the 67s and all these airplanes, and I know it's time for you guys to go. So on these newer airplanes that are not analog but digital, they may have a delay built in. I mean, they're smart enough to do all that stuff because you can't have spikes and lose your power. But analog, oh yeah, analog plane didn't care. You run into gyro, so it's didn't care.